So for the activation function, there are some strategy. This activation function is to overcome the problem of vanishing gradient problem and exploding gradient problem. In order to deal with this problem, there are some activation function that you can try. For example, the sigmoid function. When we do the sigmoid function, it is to smooth the value. So in this case, z, and we are using the e, or this is the exponent, the Euler number. The range of this value will be between 0 until 1. They call it, this is monotonic because the numbers, it will be smoothed in between 0 and 1. Differentiable, it means whether this value can be derived or not. So it is differentiable. And the derivative monotonic, it is derivative, but it is not monotonic after we do the derivative. I think, yeah, this is more in the mathematical theoretical. Yeah, we do need to understand this one in detail. But what you need to know is the range of the value. When you do with the sigmoid function, it is the common activation function because we can get the value in between 0 and 1. If you use the hyperbolic tangent, it means you are making the value wider in between -1 and 1. So the schema or the graph is similar with the sigmoid function, but the range is wider. So you can have until -1 and you can have until 1. The other kind of activation function is ReLU, or we call it, this is rectified linear unit. The value, the minimum value is 0 and the maximum is infinite. It means the maximum value can reach any numbers where the number follows with the data. If your data vary a lot, so it means if the data has a lot of variance, people usually try to adopt the ReLU. But if your data is in the similar range, for example, after you do normalization. So after you do the normalization, maybe the value of your data in between 0 and 1. Then people may adopt this sigmoid function. Or sometimes if you do the normalization with the Z normalization, it means the range of the value will be in between -1 and 1. Then you can adopt this tangent function. So the value or the activation function will depend on the data itself. This is sigmoid function. Okay. The sigmoid function is prone for vanishing gradient problem. The gradient can approach to 0 for large or small inputs. If the weights of the networks are constantly below 0, then the gradients will diminish slowly. Okay. So if the gradient diminishes slowly, then you cannot get the optimum model. Now, yeah, people try to use the ReLU because it is closer to the real value. The derivative of the ReLU is either 0 or 1. Okay, the derivative. So we can get 0 or 1. This is the derivative of ReLU. There is another kind of variant, we call it leaky ReLU. So if it is leaky ReLU, it can be negative, and if it is positive, it can be higher until some infinite value. So the error signals is also dependent on the width of the network. It depends on the width that you have in your network. If the widths of the networks are constantly below zero, then the gradients will diminish slowly. So this activation function, usually they try to avoid the value nearby zero, because if the value is nearby zero, then you cannot get the optimum model. That's why in the R and N, they have different variants. For example, there is a variant they call GERU. And there's also another variant, they call it LSTM. GRU, it stands for the gated recurrent unit. So the gated means we have a particular gate. The gate will cut the values. The gate will change the value. There's also another kind of variant, long short-term memory, or sometimes we call it, this is LSTM, long short-term memory. It deals with the vanishing gradient problem encountered by traditional RNN, with LSTM being a generalization of GRU. So if you look at this GRU, okay, the gated recurrent unit, if you still remember the X, okay, X is the input. And then, yeah, we have the H, the H, maybe this is the H0. And then we go some into a function here, and then we got a result, H1. Now, inside this one, we have a new mechanism. For the gated recurrent unit, we have a kind of gate. So we have this gate and this gate. For long short-term memory, we have this gate, this gate, this gate, and this gate. So what are those gates? This is the gates. The type of gates, in order to remedy the vanishing gradient problem, specific gates are used in some types of RNN and usually have a well-defined pose. If it is U or gate U, it is the update gate. So how much pass should matter now? So if you have a weight, we will check whether this weight, all the weights are good for the next weight. If there are some of the values are not good, then we need to update it. There is also another gate, the relevance gate. If some values are not good, we can drop or we can remove it. For get gate, erase a cell or not. So for example, yeah, in the real case, if the weight is zero, it's already zero, then you can drop, because maybe this is not that important for the next step. And the output gate, how much to refill of a cell? Because after you remove the gate or after you transform any value on the weight, the matrix might have different size. Then you need to reveal something in order to make the output equals to the hit to the hits in the next step. Okay. So we have the output gate. So if you look at this architecture, okay, in the gated recurrent unit, they have only two gates, which is the update and the relevance gate. For the LSTM, they have forget gate, update, relevance, and the output gate. So that's the difference between the GRU and the LSTM, and this is the updated version from the RNN. When RNN is only using a function, but when you use the GRU and LSTM, you have the gate mechanism. Now let's take a look on the Google Colab. For this, I'm using the TensorFlow, and there are some libraries that I will use, which is the sequential. This is to ensure the network in order to create a good network from one layer to another layer. And then we have the simple RNN. Okay, we will apply the simple RNN. We have GRU, LSTM, and we can apply some of the embedding and dense layers. Because it is about the text, now you can apply the tokenizer. It means when we have a long sentence, we can create the words. And we want to use the path sequences. So let's take a look. So this is the data. Okay, let me just use a toy. So toy means just a simple text. This is the first document. This document is the second document, and this is the third document. Is this the first document? So I will use this one. Now I'm going to check. First, it is tokenizer. Then every word will be tokenized. Then we have this is the first document. Okay. So the tokenize, I'm going to fit on the text. So the text data, it is the data. And I would like to check how many words do I have. So if you want to check this one, the total words, there are 10. Okay. And I can check the word index. The word index means, for example, the word this, okay, this is index 1. The word is, it is index 2. The word the is index 3, and so on. So usually, if we have a lot of words, we will put each of the word with index. So you can imagine if we have the LLM, okay, and if the English words, there are maybe about, I'm not sure how many words in English. If you look at the LLM with 17 billion parameters, for example, 17 billion parameters means the parameters, they also consider the index. They also consider the other kind of embedding. They consider the layers and etc. So it is very huge. Okay. So with this small index, maybe the result might not be good because it does not represent all of the sentence. But this is an example that we can look through to understand the big one later. So we can create the input sequence. Okay. It means for every of the words, we can check what will be the sequence. For example, you can create the n-gram. Okay. You can create the unigram. You can create the bigram. And yeah, let's say, yeah, it is until it is the tokenizer until the text to sequence of the line and the index 0. So it means after we have 4 lines, okay. So 4 lines means they have 4 text like what we have in our data. So we have 4 data, 1, 2, 3, 4. Okay. And then we do the n-gram sequence, and then we check what are the input sequence. Here is the token list. Sorry, I need to run this. Okay, here is the token list, and then this is the input sequence. So the input sequence means this is the index 1, index 2, index 1, index 2, index 3, index 1, index 2, index 3, index 5, index 1, index 2, index 3, index 5, index 4. So you have every part of the sequence. So this is index 1, 2, 3, index 1, 2, 3, 5, index 1, 2, 3, 5, 4. It means I know that this is the first document. If the index is 1, 4, 2, 3, 6, 4, it means 1, 4, 1, 2, 4, 3, sorry, which is 1, 4, 2, 3, 6, 4. 1, 4, 2. This document is the second document. Okay, so we can create those as a list. After we have this sequence, then you can check what is the maximum length. So this is the maximum length, okay, and this is the minimum length. So the minimum, like, make sure that you have at least 2, and then you will do the input sequence by creating the pet sequence. So if you look at this, oh, okay, I don't need to do this one. So if you want to know more about the pet sequence, you can go to this section. Okay, so someone already did example. So okay, let me just give you the example. Now we have the sequence, for example, 5, 8, 15, 12, 7, and 3, 9, 14, 6. So I'm going to make the pet sequence. So what is the pet sequence? You can see the sequence here has different length. How many components here? We have 3. How many components here? We have 2. And how many components here? We have 4. So each of these texts, they have different lengths. In order to do with the deep learning, so you need to ensure that the size is the same. If your size is not the same, then it, of course, it will need other algorithms. So let me just make it the same. How to make the same? We can use the pet sequence. So we can input the sequences and then determine how many sequence do you want for the final result. So in this case, I'm going to put 4. Then if you have 4 components, at the end you will have 4. If you have 2 components, at the end you will have 4. If you already have 4, then okay, you still have 4 components. And then we have padding. What is the padding? If we use pre, you know what is pre? Pre, it is before. It means before this number, fill in a value. So we put 0 before the 5, 8, 15. Before 12 and 7, we put 0, and 0. Okay, so this is the path sequence. Now, yeah, by looking at the maximum sequence, there are 6. Okay, so 6, 1, 2, 3, 4, 5, 6. The maximum is 6. Now, let me make the path sequence. It is the same with the maximum sequence length. It means I want to make the path sequence into 6. So if there is only 2 sentences, if there is only 2 words, then make it into 6 components. And the padding pre means I will make the 0 before. So the number will be 0, 0, 0, 0, 1, 2. The number will be 0, 0, 0, 1, 2, 3, and so on. So this is the path sequences. After we have these path sequences, now you can have the data splitting into X and Y. Okay. Now I have the X and Y, where the X is any data, okay, and then the Y is the last words. Do you know what is -1 here? This -1 means the last. The last component, it will be the Y. It means I have this text and I want to predict the next one. So using this mechanism, yeah, I have the X and Y, and then I'm going to use the number of classes. It means the total words. The total words, the one that we had before. So we have 10 words. Then it means we have 10 classes. So you can imagine if we want to create a very huge sentences. If there are 1 million sentences, then maybe the words, the total words will be more than 1 million. So maybe it is 10 million or 100 million words. Then yeah, it is highly computation. So let me just use with the 10 words. I will make the class 10 words. So you can have this one. The X is the first, second, third, fourth, and fifth component, and the 6 will be the Y. So I want to predict the next one. And after I have Y, okay, this is the Y. So the Y, we are creating the one hot encoding. Can you understand this one? This is the component. We have 10 columns. Okay. The column 1, column 2, column 3, column 4, column 5. Each column represents one word. Okay. For example, yeah, this is the word this. This is the word is. This is the word maybe document, for example. So if it is 0, then the next word is not this one. If it is 0, then the next word is not this one. This is 1, then the next word is the index 3, and so on. So we have 10 components, or we have 10 columns. It represents one word, one word. If it is 1, then it means the prediction of this data is in the index 3. If we have 1 at this section, it means the prediction word is in index 0, 1, 2, 3. Then it is in index 3. Then this is in index 5. This is the data in index 4, and so on. So this is one of the one-hot encoding. And yeah, you can do with the RNN. We use the simple RNN model. There are some parameters that you need to look at. For example, yeah, we use the sequential. So the sequential is the sequence that you will do for this modeling. At first, you will do the embedding. Okay. The embedding, it is from the total words, there are 10. Okay. And we have this 50 and what are the input length and etc. So you can look at this one. If you move your cursor here to the embedding, you can see the parameters. What is the input dimension? What is the output dimension? And what are the embedding initializers? It is uniform. What is the embedding regularizers? It is known. What is the embedding constraint? And so on. So we have the weight, we have the LoRa rank, and etc. So you can determine what are the parameters that you want to use. And then this simple RNN, I will do 100. So 100 means we have 100 times for the iteration. And then the dense, it means I will do the compression for the 10 words, and we are doing the activation with the softmax. So what we look at the materials before, softmax, it is the end of the layer. It is to soften the numbers that you got from the layers. And then do the compilation at the end with the Adam optimizer, and fit it into the X and Y. Let's do with the epoch 100 and verbose. So verbose, we just set it into 0. So it means with no verbose. So this is the model for the simple RNN. And yeah, there are many kind of parameters that you may use. For example, yeah, in order to control the algorithms, we can update the model weights based on the calculated loss. Like some of the alternatives, for example, the SGD, or we can use the RMS prop, root mean square propagation. We can use ada grad, adaptive gradient algorithm, ada delta, ada max. So this is for the loss. Here, we use the categorical cross entropy. You can determine the weights with this parameter, or yeah, if you have if your data is more on the binary, if your data is more on the binary, we can use the binary cross entropy. Binary, it is for 0 or 1. So let's say if you are doing the sentiment analysis, you want to do the prediction positive or negative, then you can use the binary cross entropy. But in our case, we use the categorical cross entropy because we are doing the multi-class classification. In a multi-class, we have more than 2 classes. What classes do we need to consider in this study? We have 10 classes. Okay, so the Y, we have 10 words. Since we have 10 words, so it is more than 2. If it is more than 2, then we need to use the categorical cross entropy for the loss. And we can use some other choices. For example, if the data is too sparse, okay, if there are many zero, you can try with this option, sparse categorical cross entropy. If you are doing with the regression, you can use MSE, MAE. And some of the algorithm like SVM, so they have another kind of choices, for example, hints or square hints. If you use some kind of matrix for the similarity, they have another algorithm, which is the KL divergence, Goldbach-Leibler divergence. It is useful in the probabilistic model and for measuring the divergence between two distributions. If you are doing with the similarity, like the cosine similarity, so you can also apply this cosine similarity in the loss. And the matrix, you can use the matrix. I think the classification will rely more on the accuracy. We can use the categorical accuracy, or you can use the sparse categorical accuracy. So it is similar to accuracy, but suited for the categorical labels, either one-hot encoded or integer label. So the one-hot encoded, it was like what you saw before, like 0, 0, 0, 1, 0, 0, 0. This is one encoded according to the column. Or we use the integer label data. The integer label data means if the word this, we use 1. If the word is, we use 2. If the word document, we use 3. So if we use this kind of integer label, we can use the categorical accuracy or the sparse categorical accuracy. For the binary accuracy, it is only for binary classification. It is to measure the prediction on two classes. And we can also use another kind of choices. For example, you use the precision, recall, F1 score, or you can also look at the AUC, area under curve. You can also measure the mean square error or mean absolute error and top K categorical accuracy. So if you have some label like 1, this is for the word this is, it is for the word, this is the label 2, document, this is the label 3. Then you can check the top K categorical accuracy. So what is the accuracy of the word this? So you can get the accuracy only for this label. The word is, so in the label 2, what is the accuracy? The label 3, what is the accuracy? So if you want to try, yeah, you can change the method or the matrix. And the activation in the simple R and N, they provide those basic one. So we can apply a ReLU or the sigmoid. We can use softmax. We can use tangent, linear, Lickey ReLU. So you can just modify the function here. So the activation you can modify with the existing what I mentioned here. Okay, that's the simple RNN. Now let's take a look if we want to make the GRU. So in the GRU, we just call the GRU. I think the remaining structure will be the same, but the architecture is different between the RNN and GRU. So let's just do this one. The other parameters are the same. Okay, the other parameters are the same. Now we are just using GRU. And for the LSTM is also, yeah, we can apply the same architecture for everything, but the insight or the structure for the neural network, we use the LSTM. Okay, with the small data, it takes like 8 seconds. So you can imagine if your data is huge, then maybe it takes some hours. Now we can try to generate the text using the train model. So after we have the model, for example, if we use the RNN, what will be the next text? If you use the GRU, what will be the next text, and so on. Yeah, this is the loop. Okay. The predicted, the predicted means we want to check the result and finding the maximum. So do you know the arc max? We want to get the index which give you the maximum values from the probability. Before we have 10 columns. Okay, we have index 0, index 1, index 2, index 3, index 4, and so on. And then we will choose the value which is the highest. Let's say the highest is this index 2. Okay, so maybe this is 0.8, this is 0.1, maybe this is 0.05, and so on. So we need to choose this one. In order to choose this one, then we use the argument x maximum. Then this will return the index. After we got the index, then we can check what will be the next word. So the next word will be added. Will be added. Will be added. Then, yeah, if you run with the simple RNN, I have only this is. So only the word this is, and then using the model with RNN, let's run until the maximum sequence length. So the maximum sequence length means I have until 6. So I need to generate until 6. And the number of words are 5. Okay, so you can have modification on the number of words. So the same with the GRU and the same with the LSTM. Then we can have this one. This is the first document. Document is. Yeah, it is a little bit strange. Okay. But this is the result from the RNN. This is the result from the GRU. And this is the result from the LSTM. This strange text happen because we have only small number of texts. Right? We have only 10 words. Okay. Of course, yeah, it will be like repetition. Some of the text will be repeated, because it has high values. So, yeah, I just give you another bigger text. If I have a bigger text, whether it is good or the same like this. Okay. Yeah, let's try. I hope it will not take so many times. So the sequence is the same with the upper side. So I will not explain more. So you can take a look on the sequence, this one. So we have the RNN, we have the GRU, we have the LSTM. And after all, after we got the model, we can predict. So let's say I have the word once upon a blah, 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 blah. What is the prediction? And let's say I have the 2 words, Jack, love. Then I need to do a prediction. What will be the next words? And I have the island, something, something. So I want to know what is the next word. Okay. Once upon a time in a small village. Okay. This is more natural. Okay. Jack loved adventures and dreamed of discovering. Okay. This is good. The islands, he got coins and okay, somehow maybe it is a kind of strange. So we need to get more data to make it better. Now let's make it longer. Okay. The word here, I just create only 5. Maybe if you create longer, it will give you a better sentence, or maybe the sentence will be more, I don't know, it is more readable in the quality, or maybe the quality is bad. Okay. So once upon a time in a small village, there was a boy named. Okay, it's a bit natural. Okay. Jack loved adventures, dream of discovering hidden treasures. Okay. So when it is very long, the model cannot generate a natural sentence. Then that's why we need the LLM. We need the big one in order to make the sentence become more natural like the human language. As you can see also this one, the island, he gold coins and ancient artifacts legend. So this is also another issue when you have only small data. Okay. Okay, so that's all about this RNN. So we learn about the RNN for the NLP and the RNN for the language models. And we also look at what are the NLP tasks for the RNN. There are some variants of the RNN and we learn from the code. This is about the RNN, GRU, and LSTM. Oh, this is the reference that I use to generate the code and the explanation. Any questions?